welcome to the 9th lecture of this course. So, today we will look at some properties of regular expression and then we will see how to convert a regular expression to an NFA. Okay. So, this will be part of the main question that we raised last time, that what is the power of regular expression, and what we said is that regular expressions are equal in power or equivalent in power to finite automata. So, the first part of showing that would be to show how we can convert a regular expression to an NFA. So, that is what we are going to see today. Okay. So, let us start by looking at some properties. Okay. So, let R1, R2 and R3 be 3 regular expressions. Then what we have is firstly the associativity law. So, R1 plus R2 plus R3 is equal to R1 plus R2 whole plus R3. Okay, so, I will write this as 1A and 1B is R1 R2 R3 is equal to R1 R2 concatenated with R3. The second is the distributive law, that is R1 plus R2 concatenated with R3 gives R1 R2 R1 R3 plus R2 R3, and similarly from the other side, if we have R1 concatenated with R2 plus R3, that gives us R1 R2 plus R1 R3. We have commutativity of the plus operator only. Okay, so this is, so if we have R1 plus R2, so this is the same as R2 plus R1, and what is important here is that only the plus operator is commutative. The concatenation operator is not commutative in the case of regular expressions. So, then we have some other identities. R1 plus phi is R1 and R1 dot epsilon is again just R1. R1 star whole star is R1 star. Okay. And okay. So, these are some of the basic identities involving regular expressions that we frequently use. Okay. So, now let us come to the question about the power of regular expressions. So, I will state it as a theorem. A a language L is regular if and only if there is a regular expression R such that L equals L of R. Okay. So basically, if I take a regular language, then there is a regular expression for it, and every language for which we have a regular expression is a regular language. So both directions. So what we will show today is the reverse direction, that is, if we have a language for which we have a regular expression, then we will show how to construct an NFA for that language, which immediately implies that the language is regular, because that is what we have seen last in previous lectures, that if we have an NFA for a language, then we can construct a DFA for it, and by definition a language is regular if there is a DFA for that language. So this is the path that we are going to take. In fact, let me just give overview. I mean, although this we are not going to look at the complete proof of this theorem today, but nevertheless, let me give an overview as to how the theorem will work, or how do we prove the theorem. So what we show today is that from regular expressions we can construct an NFA. So this is the agenda for today. We have seen earlier that from an NFA we can get a DFA. So this is using the subset construction, and what we will show in the next lecture is that from a DFA we can construct an RE. Okay, so if we have a DFA for a language, we can construct an RE which accepts the same language that the DFA accepts. So this we will see next time. So this is basically our agenda to prove this, and this will show that the expressive power of regular expressions NFA and DFA are equivalent. Okay, so let us look at the proof. So the proof of this is quite simple, and it just follows a similar pattern as the proof of closure property of union, concatenation and the star operators. Okay. So last time we had seen how to prove that the regular operators union, concatenation and star are closed. So that is exactly what the same idea will be used in this proof. Okay. So we prove this by on a case by case basis. So the proof is based on case analysis. So we will look at each different way, I mean each way of forming a regular expression. So if the regular expression is, so let us say we have regular expression over here, and what we will do is we will construct the corresponding NFA on the right hand side. So if our regular expression is phi, what is the language for this regular expression? The language for this regular expression is the empty language which does not accept any string. So the NFA can be any NFA that does not accept any string. Okay. For example, it can just be a single state. Okay. It does not have any accept state, hence it does not accept any string. So this is the first case. Then if we have regular expression which accepts only the string epsilon, what would be the NFA for it? So the NFA for this will be an NFA whose start state is the same as its accept state. So this is a NFA which has a single state having the start state and the accept state. So the string epsilon is accepted, but no other string is accepted by this NFA. If we have the regular expression A for a some symbol in the alphabet. Then our regular the NFA for it will be, we have a start state, and from that we go to an accept state with the label A on it. So, if we see the symbol A, it gets accepted, but no other symbol is accepted by this NFA. So, these are the base cases. Now, what about the inductive cases? If we have a regular expression R1 plus R2, by induction we assume that we have an NFA for R1. Okay. So, let us say that this is my NFA for L of R1. So, this NFA accepts the same language as L of R1, and we will assume that this NFA has a unique start state and a unique accept state. So, let us call this Q1 and let us call this R1. Okay. If you look at the NFAs that we had constructed earlier, each one of them had a unique start state and a unique accept state. I mean, here we can actually add an accept state also if you want, basically with no transition from the start state to the accept state. So, it is just an empty. So, we have an NFA for L of R1, then we have similarly an NFA for L of R2. Now, using these two NFAs, I construct another NFA which has a unique start state. Let us say I will call it Q with epsilon transition to Q1 and Q2, and it has a unique accept state, I will call it R, with epsilon transition coming from R1 and from R2. Okay. So, if you look at this NFA, every string that is there in either L of R1 or in L of R2 is accepted by this NFA, and by our to preserve our assumption. So, to maintain our assumption, this entire NFA has a unique start state and a unique accept state. So, we can keep building it recursively. So, starting from these three base cases, I can build an NFA for a regular expression which has the plus operator in it. Now, you can very well guess what would be the NFA for R1 concatenated with R2. So, we have, let us say, an NFA for L of R1 and we have an NFA for L of R2. Okay, so these are the start and accept states. I add a global start state and I have a global accept state, and I just connect using epsilon transition. So, from this to this, from this accept state to this start state, and then from this accept state to the our new accept state. So, this is the NFA for L of R1 concatenated with L of R2. And finally, for R1 star, let me just write it as R1 star. If we have an so let us say this is our NFA for L of R1, I add an epsilon transition from the accept state to the start state of that NFA. I add a new start state and a new accept state, and I add epsilon transition from here to here, and from here to here. Also this is a epsilon transition. So, in both these cases we have an NFA which has a unique start state, a unique accept state, and it accepts the required language. Okay. So, this proves that given any regular expression, okay, I can look at each part of that regular expression, and in an inductive manner I can construct an NFA for it which accepts the same language. Okay. So, finally, what we will see today is what is called a generalized non-deterministic finite automata. I will just give the definition of it. We will see more about it in the next lecture. So, a generalized non-deterministic finite automaton. Okay. So, in short, this is also known as a GNFA. So, a generalized non-deterministic finite automaton is a non-deterministic automaton which has regular expressions labeling its transitions. Okay. So, in a standard non-deterministic finite automata, the transitions either have symbols from the alphabet, the input alphabet, or it has epsilon, but it cannot have anything else. But suppose if I generalize this idea and I allow a non-deterministic finite automata to also have regular expressions on its transitions, that is what gives a generalized non-deterministic finite automata. So, a GNFA is a NFA that has regular expressions labeling its transitions. Okay. So, just let me give an example. So, here is a example of a GNFA. So, we have, let us say, a start state here, I will call it QS. We have a state Q1, Q2, and let us say Q accept. Okay. And suppose we have transitions from Q start to Q accept with the regular expression 0 0 star, from Q start to Q2 with the regular expression phi, Q start to Q1 with the regular expression 0 1 star, 1 1, 0, Q1 to Q2 with the regular expression 1, Q2 to Q1 with 1 1 star, and let us say Q1 to Q accept with the regular expression 0 plus 0 plus 0 1. Okay. So, this is an example of a generalized non-deterministic finite automata. It has transitions whose labels have regular expressions on them. So, let us look at a few strings which are maybe accepted and some strings which are not accepted. So, if we look at the string, if we look at the string 0 1 1 0 1, is this accepted or not? Okay. So, how can we get this string? So, basically the way a string is accepted is by, so can we partition this string into pieces, into parts, such that each part is basically in the language of the regular expression of a transition, and concatenating them I get a path from the start state to the accept state. So, one way of going getting q 0 1 1 0 1 is if I take 0 1 1 from here, because I have 0 1 start. So, from qs to q1 I take 0 1 1, and then from q1 to q accept I take 0 1. Okay. So, one way of going is I go from q start to q1 by matching with 0 1 1, and then from q1 to q accept I take the string 0 1. So, this is one way. Maybe there are other ways also. For example, what I can do is I can go from qs to q1 on the string 0, okay, because this has 0 with 1 star. So, I can take 1 star as epsilon. Then on q1 I have basically a self loop with a 1 1 on it. So, from q1 I stay at q1 on 1 1. So, this gives me 0 1 1, and then from q1 I go to q2 on a 0 1. Okay. So, I can form 0 1 1 0 1 in these two ways, and if you look I can actually form via other ways also. Okay. So, there are other ways by which I can form the string 0 1 1 0 1. Okay. Now, what about another string, let us say, okay. So, hence this string is accepted. So, what about a string 1 0? Okay. So, if you look at this regular expression, you realize that there is no way I can go from q start to q accept via a sequence of transitions, which will give me the whose concatenation will give me the string 1 0. Okay. So, there is no way I can do that. So, no way of going from q start to q accept forming the string 1 0. Okay. Hence, this string is not accepted. So, these are two examples, and this is basically what a this is the way a GNFA accept or does not accept say string. So, the reason why we are looking at GNFA is because next time we will see that when we convert a regular expression, when we convert a DFA to a regular expression, that is where we will use the power of a GNFA. We will use GNFA to allow us or to enable us to construct a regular expression from a DFA. Okay. So, I will stop here today. Thank you.